Alright guys, welcome back to another recording on bonds and determining types of bonds. And now we're going to focus, we talked about ionic, we talked about the lattice energy being what holds together an ionic bond. The strange thing when we talk about ionic bond in relation to everything else, it is the strongest bond that exists. It is the strongest intermolecular forces that exist. So in relation, it's kind of weird because it's a bond, but then the way things situate in the crystal, it also is considered a strong intermolecular force. And the force is lattice energy. So keep that in mind as we go through covalent bonding and what makes up all those different types of covalent bond that we talk about. Because remember, we talked about polar, nonpolar, and coordinate covalent. Okay, so those were the three we discussed back above. Now we're going to look deeper into the covalent types of bonds. All right, so looking at this, I'm going to emphasize this all the time. When you are faced with any question with bonding, and it asks you the type of bond or characteristics of the bond, the first thing on any of these problems that you have to do is the thing that's on the top of this paper. You always have to ask, what is making the bond? Because regardless of the difference in electronegativity, if you have a metal with a nonmetal, we say that is ionic. It'll have varying ionic strengths, character strengths. How high will its melting point be? How hard will its crystal be? That'll be based on the lattice energy. It'll also be based on that electronegativity difference too, because usually the greater the electronegativity difference, the higher the lattice energy. Usually. Okay, I'm going to stress that. Usually. Not always, but usually. Just keep that in mind, because it's very hard to go with absolutes. It's Mother Nature. There's always a twist to it. It's really hard to, man always wants absolutes. This is a rule, follow the rule. Mother Nature has her own set of rules. And again, I'll always try to teach this to you. Mother Nature is Mother Nature. Mother Nature is the judge and jury. You break a rule of Mother Nature, you don't get to plead your case for a lesser sentence. She'll sentence you, discipline you, have the effect of your actions that you have to account for be to the effect of how greatly did you violate her natural law. And I use the word her, loosely here, because who's to say it isn't Father Nature, okay? So keep that in mind, because absolutes don't necessarily happen when you talk about science. We try to make them happen, because we're man, but it doesn't always happen. So, going on to covalent bonds. Remember, with covalent, you're looking for a telltale sign to set off a little bell ringing in your head, is that you have a nonmetal with another nonmetal. Okay? So if you see that, we're now in this realm here of covalent bonds. And we have, again, two different types of covalent bonds. One that share equally, one that shares unequally. Okay, there's a pull on them. When you have a covalent bond, because they're sharing, you have different ways to share, depending on how many electrons a particular atom in the bond wants or needs to fulfill its octet. Okay, so that's the big deal. So, you can have what's called a single bond. A single bond means, if we look at H bonded to H, there is only one pair of electrons shared between them. Okay, now bonds, electrons, and bonds can be represented two different ways, which is a little bit below where it says, understand this line, right? That line is the same thing as two little electrons drawn above each other being shared. So there are two ways, and both of them are considered the Lewis dot way, to show bonding. Okay? And when you have a multiple bond, then you put another line. So this is a double bond. And if I wanted to have a triple bond, if we go all the way over here to where nitrogen is, see how there's 3 lines in between them? 3, triple bond. Okay? So we can have these 3 different types of modes of sharing depending on the atoms making the bond. You can share 1 pair of electrons. You could share 2 pairs of electrons, which are 4 total electrons shared. Or you could do 3 pairs, which are 6 total electrons shared. Now, that brings up my little statement down here about careful with wording. Wording of your questions. Are they asking for how many shared pairs or how many shared electrons? So this is what I mean. It's like, what are they asking for? Asking, oops, oh, that's right, I forgot I don't have my little thing on. Asking for shared pairs. And then you're looking for how many lines do I have? How many sets do I have? Or are they asking for shared electrons? Because then your total number. So that's what this little baby means about careful with wording. You gotta slow your brain down about, I gotta read this really fast because I go really fast because I gotta answer a lot of questions, to making sure you're really reading the question so you can answer it properly. Because they're gonna give you both answers to see, did you read the question? They'll give you the number that, let's say they wanted shared pairs. They'll give you the numbers for shared electrons as well as shared pairs. Okay. I'm going to tell you right now, it is really important, and we're going to learn why it is this way, not during this topic lecture, but the next one. Okay, so not Thursday night. He is going to hate me because you're going to have this one. And then I'm going to say, yeah, it's a long weekend, so Monday night I'm going to have you do another one. Okay, so this one right here is oxygen, and oxygen always has a double bond. Nitrogen always has a triple bond. Hydrogen's easy to figure out, it's a single bond. But oxygen and nitrogen you're going to need to know. You're going to need to know when they talk about something that has a double bond, that is oxygen. There's some other ones we'll learn that they'll always ask you about, like carbon monoxide. That has double bonds. You'll get to know that because you're going to draw it like crazy next week. Okay? And you can say, draw it. Oh, yes, draw it. So keep those in mind. Start really visualizing these. And we'll get into why does it have a double bond? Maybe tomorrow. No, sorry, that's right. I keep forgetting. No school Friday for you guys. So it would be the Tuesday. We'll get into it. Okay. So, lengths of bonds. Down below, the amount of electrons that are present and the pull between the nucleus of one atom to the electrons of the other atom. Okay, so now this is different. This isn't Coulomb's law with relation to an outer electron to an inner nucleus. It's actually the attraction between, which can also go still by Coulomb's law, the nucleus of one atom to the outer electrons of the other atom involved in the bond. Okay, so depending on how many electrons, the distance, etc., you can have different strengths to the bond. In general, I'll keep using that word, in general, the single bond that is between two atoms will be the weakest bond. It is also the longest. And boy, I can't tell you how this is used very often to explain and justify your answer. Okay? Knowing this, saying a single bond has the longest length, and therefore it's the weakest, so it will take the lowest energy to break because it is the weakest. A triple bond is the shortest, and it is the strongest, so therefore it will take the highest energy to break out of covalent bonds. And then ionic bonds, because it's a lattice energy and it's a strong positive and negative attraction, not a shearing, have even more strength than a triple bond. Okay? So this is important, and you have to be able to get it into your brain in such a way that you can explain it, because often that is the justification to a lot of questions about bonding. All right. The more bonds you have in between two atoms, the closer they get pulled to each other, the shorter the bond length. Really good to know. Going further down on this page. And I'm going to quickly go through this because we will come back to this. Very simple plugs and chugs later on when we do energy. For now, I'm going to show you this broken minus formed thing, because remember we talked in the last lecture about, erase the crap from bio. Let go of the crap from bio. Bio looks at things so strangely and sometimes incorrectly that you have to realize putting energy in breaks a bond, and you need to break a bond first. Then you can rearrange to make a bond later. Okay, so it is important to understand that. Usually when you do energy, you do products minus reactants when you have certain tables. In this table, it's a bond energy, individual bond energy. So that's a big thing to know, that this is individual bond energy. Okay, it's a bond energy. Bond energy. And you might say, well, why are you making such a big deal about that? Well, we'll learn in 3 months from now about a whole compound's energy. And so you have to be careful which way are you doing it. Are you doing compound energy or individual bond energy? So if we are doing individual bond energy and we want to know the whole energy of the system, we use this little thing down below where we talk about bonds broken minus bonds formed. Okay, and that's a big deal. So you literally go through and look at how many. So I used the example before at the beginning of this discussion on what is a bond and breaking and formation. Right? I used H2 plus Cl2 gives us 2HCl. So I have an HH bond, I have a Cl-Cl bond. They're the ones that are broken. So I would go back up to this table and plug in the values. Now I didn't do this here. I'll do it off to the side so you can see that you can actually calculate this out. An HH bond, as we look up above in the table, is 436 kilojoules per mole. A Cl-Cl bond, where are you, my little friend? Oh, maybe I don't have it in this table. Oh, here it is 242. So, and if I wanted to find how much energy, and we call it delta H, the heat of reaction. And the RXN down here stands for reaction. Action. All right? Reaction. So I know it's strange, but chemists hate to write. And I told you I hate English, so part of the reason why I'm a chemist. So I have the left part of this equation right here. That's breaking. So it's 436 plus 242, and then I'm going to minus, and this is what you have to be careful of when we get to do it. I have 2 of these, so I'm going to form 2 of the HCl bonds, and my HCl bond is 431. Now just looking, I'm not going to do the calculation, but guys, just looking at it, I have 2 numbers in the 400, and I have a 400 and a 200 and something. So this is going to be over here less than this. So my number is going to be negative, which means this reaction is really favored. Okay, it gives off energy. It produces energy. Right? Breaking this bond doesn't. Breaking this bond doesn't. And you add those together, and even that total over here isn't going to be enough to suck in energy, use energy, need energy. Because when you make this guy, you release so much energy, the net overall is a release. Okay, and that's the thing that you don't get taught in bio. So you're misled. Yep, I'll slam bio every day and every chance I get. Not that I hate bio, because I think bio is absolutely fascinating, but I only think it's fascinating when I approach it from a chemistry endpoint. Okay, I just have a chemist view on bio. I never, ever took a biology course. never took a straight biology course. My biology courses consisted of biochemistry and genetics. That was my required bio that I had to take. I never took an intro bio course ever, not even in high school. And I'll explain it sometime. And if I don't, remind me and I'll tell you the story. Okay, so now we're going to look at bond polarity because we're talking about covalent bonds. And covalent bonds are two nonmetals coming together. And we learned the other day that you can have two nonmetals that are exactly the same, or have very little difference in electronegativity, or you can have ones that have a big difference and they're unequal, or you can transfer your electrons. So we learned all of that the other day. Right? And I have the words highlighted here again. So equal sharing for nonpolar, polar is unequal sharing, ionic is transfer. Try to keep that in your head. Regions just sticks to this. They don't even go into numbers very much. But AP looks at the electron cloud density. So down below, where you've got those funky little shapes in the middle, and it talks about your bond polarity, this is what we call electron cloud density. Come on. I think I'll change, and I'm going to make it a little bit thicker, because on this particular drawing, unlike the other one, it seems to get really thin. Okay, so these little diagrams here are called like electron cloud density. Where do the little electrons spend time? When you have two things, right, we have two atoms here. We got a fluorine nucleus and a fluorine nucleus. They're exactly the same. So when an electron is buzzing around, there is no preference to where it is in space. So after they plot all of this, and I should have changed my color for my electron. So since I've been hitting my little electron there, I will change the nucleus to red. Okay, and then we'll go back to the funky little electron. Okay, so the electron's buzzing. And it's just moving around all over the place. And over time, when you look at it, you have what's called an even distribution between the two nuclei. There's no pull in either direction because the nuclei have the same amount of protons in them. Now, if I change one of these, and instead of being F bonded with F, I decide, oh, take that out, and I'll make it hydrogen. So now I have H bonded with F. Right? And guys, do not get hung up on, you might say when you go from here to here, oh, she changed the wrong letter. These rotate in space. They flip around. They spin around. They tumble. We're taking a snapshot of time and then recording it on a piece of paper. And when we get to next week, we're really going to talk about what is its three-dimensional geometry. So, yeah, I crossed out this one, but then I wrote the H here. But I can pick this baby up and flip it over, and it will look like this. And they're exactly the same. Because in 3 dimensions, it just keeps tumbling. So try to get past our 2-dimensional view. Try to get your mind to let go of some conventions. You can't be rigid. You got to kind of think in more ways than one. When we look at H with F, now our little electrons do something different. So now I've got my hydrogen nucleus. Now these are the nuclei. This isn't the whole atom. And now I'll use yellow. My little electrons, because of electronegativity difference, this one's got a much higher electronegativity value, right? We say it's set to 4. And you start to look, and the electron goes, oh, I'm going to hang around him because he's cooler. Spends more time, and then comes over here. And then it hangs over here. And then we'll do a little buzz by there. And then we go over here. And then it buzzes over here. So the density starts to get very high over here, and we call it a pull on the electron. The nucleus here will pull on that electron that are around this hydrogen more, and it will pull them in, and they'll want to hang around the fluorine more, and you have a flow of electrons. Okay, so we call this a flow of electrons. We call it a net flow. In this case, it goes towards the fluorine, hence the arrowhead pointing towards the fluorine. And remember, this is a partial negative because it doesn't transfer. It does a lot of buzz arounds, and then it goes and it does a flyby on the hydrogen. And then it buzzes a lot around the fluorine, and then it does a flyby the hydrogen. So this looks partially positive because it's sometimes exposed, and this one's almost always covered, so it's sometimes negative. This is very different than using my crystal here. This is your ionic crystal, where you really get an exposed nucleus, and I shouldn't say nucleus. You go down to the core, and you lose your outer electrons. So the outer electrons transfer this way. This is just your core. And it is a transfer. So then you have a true charge. You have a positive on one and a negative on the other. Okay, that's ionic. So we're going to talk about these intermolecular forces and all this attraction and what does it do and what's stronger and what's weaker. And then we'll revisit it again when we study states of matter, because those intermolecular forces are what create the various states of matter, how you change from one to another. So that's really important. Okay. Right now we're just going to focus on, if I'm given a bond, can I tell if it's polar or nonpolar or ionic? That's our focus right now. Okay, there's a lot of things interwoven with the bonding, but right now, when we get through like this weekend, you should be able to tell me if something's polar, nonpolar, or ionic. And really, we'll go a little further, and you should be able to identify metals alone. So you should be able to get those 4 types of bonds set in your brain. Polar, nonpolar, ionic, and metallic. Okay? So looking at this just goes through and says, well, what do we look at when we are asked to determine what type of bond is it? Well, first, I always ask, is it a metal? Oops, I gotta go do this again, I'm sorry. Do we have a metal with nonmetal? Or 2 nonmetals? Because that sets you down one pathway or another. Right? Because if it's this, it's ionic. If it's this, we got to ask another question. Are they the same nonmetals? Or 2 different ones? Because if they're the same, the only thing this can be is nonpolar. Okay? If it's 2 different, you kind of have to ask how different. And then if we're greater than 0.4, we're definitely polar. But there, I will argue with you, and so will a lot of other teachers say, I don't know where that cutoff comes with for AP, because you will always have a little polarity once you get to 0.1. They're saying it's not strong enough to give it huge polar characteristics. Don't forget, we're going to have the scale then. If I'm in this range, I'm considered nonpolar. If I'm in this range, I'm considered polar. If I'm greater than 1.7, I'm considered ionic. Are there exceptions? Of course there are. Let's take a beauty, the one above, HF. Okay, this is 2 nonmetals. But I'm going to tell you, that is considered polar covalent. It is not ionic, there is no transfer. But if I do an En difference, I have 4 minus 2.1, which gives you 1.9. 1.9 falls in here. But this is not ionic. It's not, guys. It is polar covalent. So I always tell you, and will always say, this question is the most important in determining what makes a bond polar or non-polar, not polar or non-polar, polar and ionic. Okay? Once you get past the polar and ionic, then you can kind of get nitty-gritty about non-polar and polar. But it's really metal with non-metal or two non-metals. And down below, these are all different types of molecules, and you're looking at the flow of the electron density, right? If we have the flow, see how this guy's got more density than this one, then the flow is this way. Okay, that's polarity. This is evenly distributed, no flow. Okay, no net flow. This has flow. This is no net flow. This has net flow. Okay? That's what you're looking for. And this just goes through. You can copy the stuff down on the bottom right. I'm going to move it up. Now, we have an analytical technique like PES, like your ultraviolet spectroscopy, UV vis spec. We have a new one now. And this is called infrared, using the wavelengths in the infrared region of our magnetic spectrum. It hits the molecules with all this broad wavelength. And it is a stream. If you look down here, the wavelengths go from, come on, here we go. And they go from 4,000, this is a wave number. They convert it to wave number. So you go from a wavelength to another wavelength, and you scan it during that wavelength. I have to go and convert them. So it's 1 over 4,000 per centimeter, and then that's really your frequency, but it's not per second. It's how many wave numbers you have, and I'll convert it to wavelengths. I have to look up its conversion. It's how the instrument measures it. But what you do is you measure how much energy gets transmitted through. Okay? Now, are you going to need to know that that's actually what you measure? No, not really. What you need to know is that it tells you structure. Right? By measuring this transmittance of energy, okay, it can tell you certain things, because we have what they call stretching, meaning this, you have oxygen, and I changed my pen here. You have oxygen bond to hydrogen. This bond will go longer, and then it'll go back in and get shorter, and it'll go longer, and then it'll go shorter. And that's called a vibration, and that's a stretching vibration. And then you'll have a carbon hydrogen that does that. And then you have a different type of carbon hydrogen because it's bonded differently in this molecule. And when you look at this molecule, you have a carbon to a carbon to a carbon will make these, okay? And then there's an H and an H here. And these will vibrate back and forth close to each other, as well as in and out. And that's what the IR measures. It measures how much movement this way, back and forth, and then how much movement this way, back and forth. Okay? So it's hard to explain, because unless you get to run a machine and see it work and see it scan and come up with these, it's really hard to wrap your brain about what's going on. But this is what it tells you. It tells you this thing called a functional group in the molecule. That's what it tells you. It tells you what's attached what structure is there. Okay? So PES tells you structure of an atom. IR tells you structure of a compound. Okay, that's the big difference. PES is for the atom, an individual atom. IR is for a big compound. So if you do any type of synthesis work, you run IRs to check to make sure that if you wanted to put in an alcohol, you have, this is alcohol stretching right here. Oh, look, I got the alcohol. And that's what you use it for. Okay? So on the next page, it tells you, this is the big thing that it's used for. Right? This is the huge big thing that it's used for. And that is a major aspect of IR. Remember, you're going to have to know them. We'll refresh our memories when we go to study for the AP and review. But you have to know all those things that are on the back of your previous note packet, the last page, where it had all the frequencies, and then there was all the different types of analysis you can do. So we've talked about something that's in the infrared spectrum now. We talked about stuff that was up at the X-ray. We talked about UV vis. We're going to talk more about MRI, not very much though. So you have to know, when do I use it? If I want to know, what interacts with what, I might use MRI. If I want to use a pure atom structure with electron, how much energy to kick out an electron, I use PES. If I want to use, do I have certain functional groups attached, I use IR. And that's what you have to know. Okay, so it's a shorter video for that tonight.